All right, everyone, welcome to our AI Trends 2024 series. As you know, each year we invite friends of the show to join us to recap key developments of the prior year and anticipate future advancements in several of the most interesting subfields in AI. Today, we're joined by Kamyar Azizzadenesheli, research staff at Nvidia, to talk about all things reinforcement learning. Kamyar and I last spoke a couple of years ago for our Trends 2022 series. Of course, before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. All right, let's jump right in. Kamyar, welcome back to the TWiML AI podcast.
Yeah, thank you so much. Thanks for having me back, Sam. And it's a pleasure to be here talking about reinforcement learning, AI, and new tools and new technologies that are pouring into reinforcement learning that are going to shape the future of reinforcement learning. I'm glad to be talking about these subjects with you.
All right, so Kamyar, let's maybe get started with your general take about 2023 as a reinforcement learning researcher. I think clearly a lot of excitement in 2023 has been focused on LLMs and generative AI, and you kind of get a couple of reactions, at least on Twitter. There's the one, hey, there's other research happening in AI, but then there's another reaction, which is really, LLMs have implications broadly beyond just chatbots. Let's embrace this and see what we can do with it. I think I know what your answer is based on some of the themes that you prepared for our conversation, but I'd love to hear you just kind of riff on how the year felt as an RL researcher.
Yeah, that's a very fascinating question, and also a fascinating time to be working in reinforcement learning while having ideas of classical reinforcement learning, the topics we have been developing since like 40, 50 years ago in this field. Uh, One of the major theme of this year and also the future theme of reinforcement learning is upon this creation of LLMs and generative AI tools, in the sense that we now can use these tools as a means of knowledge abstraction, I would say.
Hmm.
These models, yeah, they are chatbots, but at the same time, they are extremely flexible. They are multimodal, and they are able to generate not only text but images and videos and create imagination for AI agents. And when you enable such an imagination for AI agents and provide layers of abstractions for AI models, we can use these to frame novel and new foundational reinforcement learning principles, basically. So it means that if I want to train a reinforcement learning agent these days, I don't need to start from scratch. We can actually use the power of these LLM and generative AI models to instruct the AI agent. So AI agent doesn't need to, or reinforcement learning agent doesn't need to go all the way down and do all the exploration and exploitation and learning and try and error all by itself without having much abstraction in the knowledge related to the task at hand. Given these LLMs these days, we can actually use these LLMs to instruct these reinforcement learning agents to tackle hard tasks. It means that we can actually go after many tasks that before were out of reach because we didn't have right level of abstraction. This is going to unleash so much of research, and I'm very excited about it. It had started. There are so many works these days that researchers and colleagues that develop methods which uses these large language models and generative AI models to do reward design and break down the tasks, navigate robots, navigate AI agents or reinforcement learning agents in complex domains. And this actually enables us to take leaps that I would say we thought for a while we're like way out of reach, but nowadays we're getting there, and I'm very excited about that.
Awesome, awesome. I'd love to have you talk a little bit broadly about 2023 and kind of how that shaped up as a year for RL research. Like, just in broad generalities, was it, an exciting year with lots of breakthroughs, or was it a boring year? What was your general take on the year?
Okay, that's a great question. I want to answer this question from two perspectives.
Yeah.
One of them is from a theory perspective. One is
Okay.
from practical, empirical study perspective. From
Okay.
theoretical standpoint, we have been extremely excited because having LLM in our formulation of reinforcement learning enables us to go and develop foundations given LLMs.
Okay. So is it kind of rewriting all of the theory to
Yeah,
be, old stuff plus LLMs?
exactly. So we want
Okay.
to reshape and reformulate reinforcement learning. I can tell you, in
Yeah.
1995, we were talking about hierarchical reinforcement learning a lot,
Right.
like every
Right.
day. I mean, I was not there, but my colleagues and friends were there, and thankfully, I had enough time during my PhD to read so many of the old literature. We were talking
Yep.
about hierarchical reinforcement learning, abstraction in reinforcement learning. All of them were like hypothetical, and all of them were uh, based on these assumptions that there exists in hierarchy that we can extract.
Mm. And so now we actually have a tool that lets us do that.
Exactly. Now we have a tool. It literally allows us to do that. And this is from theoretical standpoint. We will reformulate reinforcement learning condition to the fact that we have access to LLMs, and this
Okay.
has great implication. I can give you examples. That's what machine or what reinforcement learning agents would have done before LLM, and now
Uh-huh.
with LLM, how they would tackle problems. So what I like, let me give the example
Before we do the
here.
example, you said there was the theoretical perspective and then the practical perspective. What's
Yeah.
the practical perspective on that?
So for the practical perspective, now that we have this LLM, we can do so much. We can develop so many new RL deep RL agents, basically that they
Mm-hmm.
can tackle extremely hard and challenging problems.
Mm-hmm.
And another aspect that it actually unleashed is the interactive learning of reinforcement learning agents and robotics. Now, before, but in the past, we were if you wanted to train a robot, we had a design task and the designed goal plus the cost functions, and the agent we would use to like optimize the agent to tackle that task. Now we can interactively talk to the robot, helping the
Mm-hmm.
robot to explore the world. We can actually tell the robot, hey, first, in order to accomplish this task, you need to first go there, and from there you need to go to other place and sequence all of these tasks or all of these steps while just talking to the robot. We don't need
Mm-hmm.
to go down. Like the abstraction is like we can actually have a communication with the robot to get to the goal of training. So that's a second thing in reinforcement learning, that we can have interactive interaction with RL agents and
Mm-hmm.
bring LLMs to design reward. This is very important. We now can have LLMs to design rewards for reinforcement learning agents. So not only they can instruct the reinforcement learning agent, they can also instruct them. Sorry, they also can design the reward. Both LLMs and generative AI tools design reward for RL agents to accomplish very hard tasks. So
Mm-hmm.
that's from practical standpoint that many of colleagues and friends are working on this, and I think 2024 we will get it. But for the future steps of reinforcement learning, we will have a lot of these things.
Okay. If I can try to paraphrase two aspects, one, and this isn't necessarily the theoretical versus the practical, but I heard kind of two important things in there. One is that LLMs kind of bring to the table a world knowledge, if you will, that RL agents didn't previously have, or they had to build up from scratch, from nothing. We remember seeing the videos of like RL agents kind of, banging their heads against the wall, so to speak, in games, trying to figure out like some basic things. And now, as we'll talk about in some of the examples that you curated for us, they're able to start from a higher level and access this, essentially a database of the world, or a reasoning engine about the world, via that's provided by LLMs. So in a sense, it's the advantage of, or the power of pre-training that we've seen in so many places, in other aspects of AI. The second thing that I heard you say is that LLMs can be integrated into reinforcement learning such that they, I guess, provide more intelligence to the way we direct the agents kind of internally, more of a structural impact or structural influence on the way the agents behave through manipulating the reward or the objectives based on their knowledge of the world. Is that a good summary of some of the key ways that LLMs have impacted RL?
Yes, yeah, that these are basically the two main things: the global knowledge abstraction that they have about the world,
Hmm.
and the fact that we can use them to instruct RL agents.
Awesome, awesome. So you mentioned that you had a couple of examples to give to illustrate this for us.
Yeah, the first point that you made, the fact that they have knowledge of the world, and the fact that all their RL agents, they were banging their head against the wall and they were doing random stuff. So one
Hmm.
example of this one in reinforcement learning realm is, consider a kitchen and a robot or an RL agent there, and the task
Hmm.
is making pasta.
Yeah.
Okay, so that's the whole thing, and all of this I could communicate with words with you.
Hmm.
In the past, okay, I'm going to be a little bit exaggerating here to make the point,
Fair enough.
but in past, the RL agents, when we were putting it in the kitchen to accomplish such a task, and we had a reward function there, which is like, if you cook a pasta you get a reward 1, if you don't,
Hmm.
0. The RL agent, both in theory and also in practice, could have thought of making an airplane in the kitchen as a possibility of the action space.
Hmm.
So the RL agent had no idea about abstraction of the word. It was a plain like plate, starting from scratch, not knowing anything about the world or any understanding of what is even pasta.
Hmm.
It was mainly through trial and error. The agents we used to make for Atari games had no idea when they were starting. They had no idea about the game or what is the thing they are dealing with. They had no understanding or abstraction of the environment. So at this point, now that we have these LLMs, they
Hmm.
can literally break down the task of cooking pasta in the kitchen. They would not instruct the RL agent to consider making or creating or building an airplane in the kitchen as a possibility of potential outcome.
This makes me think back to one of our earliest conversations about RL. I think the way I remember you describing this is that one of the key challenges in RL is making the problem tractable by kind of carving up the space of possible things that, or limiting or constraining the space of possible things that the agent can do, so that you don't have to try everything. And what LLMs do is give the agent like reasonable things to do, as opposed to having to try every possible action to achieve the goal.
Yes, exactly. That's actually the case, and is it's the point you made was literally what is happening in the past. We knew we need to narrow down this state space. We knew that we need to narrow down the space of possibilities. We have so much theory and philosophical thoughts about it, but we didn't
Hmm.
have that abstraction to do it. Now LLMs
Hmm.
would give us. Now LLM says, you want to make pasta? Don't do explore everything. Just
Hmm.
go to the, I don't know, cabinet, take pasta out, uh, boil water, breaks down the task for the agent, and
Mhm.
agent is going to solve the subtasks. And even for the solving a subtask, the LLM or the generative AI models can go and instruct the agent. So this is fascinating.
Mhm.
Let me tell you what I mean by instructing.
Mhm.
The the LLM can ask the or RL agent accompanied by LLM model can go and break down the task of making pasta to many subtasks. And
Mhm.
for each task, let's say the first task is going to the door of like the fridge. So
Mhm.
that's the first task. So
Mhm.
this task of going to the fridge door, I can write in words, and generative AI can think about what that would look like, right?
Mhm.
And the RL agent goes and does something, and then we can use LLM to describe what the agent has done. And if the
Mhm.
thing that the agent has done, which is like a video, right, the RL agent goes and does something,
Yeah.
we can see it, record it, give it to the Gen AI. Gen AI model or LLM would give a caption. And if the caption doesn't align with what has been asked, you're going to lose points. So this way, you can
Mhm.
actually use uh, these techniques, these models to instruct RL agents
Mhm.
easily. And
Mhm.
so you break down the task first using the abstraction, or knowledge of the world that LLMs have. And then after that, for each piece, or when you break down the problem to smaller pieces, for each piece you can actually use LLMs to instruct directly the RL agent to accomplish the task. So this is basically one of the um, intuitive example, but theoretically
Yeah.
we given some other examples. An example is like, let's say your task is to get to the door of my apartment,
Mhm.
and there's a key on the table. RL
Mhm.
agent before LLM would have tried all possible ways
Let
to
me try
get
to
to the
open the
door.
door with the chair.
Yeah, literally that would be one of the ideas, and
Yeah.
they would just but for first millions of time steps they just sprint to the door.
Right.
They don't if the task is to get into the door, they just sprint to the door and they don't even look at the key. But if they
Mhm.
know, if LLM tells them this knowledge of or concept of the key, the problem is going to be solved in two steps. So this is what makes me excited about bringing uh, this to reinforcement learning.
And you identified a couple of papers that were good examples of this kind of integration of LLMs into the field. And your examples really remind me of the Voyager paper most directly, which I thought was super interesting. Can you talk a little bit about, give us an overview of that paper?
Yeah, that's one of the earlier works in this direction. The field is full of smart people. They come up with we actually the field the people the researchers come up with many great ideas to develop models, reinforcement learning models that utilize these LLMs.
Hmm.
And in this work and a few other works that are doing similar approach, you can actually use LLM to generate codes that when you compile, your agent does the job you want. So
Hmm.
your LLM generates a code, your agent does something, and then you ask whether that thing was right or not. If it was not right, you actually tell LLM to tweak the code. So it's like
Hmm.
LLM is actually going directly, not only instruction by language, it actually goes and code up the RL agent what to do. So that's very fascinating.
What's the role of this code in the Voyager paper?
So the code can tell you that if you hit a wall, what to do.
Hmm.
If you have a hammer in your hand, this is for uh,
Minecraft?
sorry for Minecraft. And
Yeah.
if you have a hammer and in front of you is like I don't know a gem, go with it and just break it down. If you're seeing a beast and you need to switch your tools to something else and go to like a fight with the beast or take the beast down. Or
Hmm.
if you see I'm not an expert in Minecraft, but if you see something cool that needs to be done to gain something, the agent would just go and do that. So that's basically the code level. So you don't train, let's say, DQN model for the RL agent. You'd literally go and code it up and say, if you see this thing go up, or if you see this thing go down, or
Huh. Interesting.
break it down, or change your tools, or gain new tools, or put something in your uh, bag or something like that.
Yeah, I didn't fully get the role of the code. I thought it was super interesting that code was being generated. I didn't realize that it was replacing the traditional RL algorithms. There are some great examples of similar to the ones that you gave, but essentially the model has, or the I guess the model will take the inventory of, you have a bunch of tools like planks, a stick, crafting table, and a stone, and that's given to GPT-4 in this case, and then GPT-4 is providing a task that moves the agent towards a broader goal. So incorporating the idea of curriculum learning. So as opposed to giving it this end goal, like just do this next task. I know one of the things that really struck me about this paper, which is I guess I'm trying to get to, is that it incorporated not just LLMs, but a lot of disparate ideas that we kind of talk about in the context of RL, like curriculum learning and this, interactive prompting, and a bunch of different things to create this model that ultimately seem to do better in terms of collecting different things in Minecraft. Again, I don't know Minecraft very well, but that seems to be the metric that they were optimizing for.
Yeah, I can imagine, like, this curriculum learning basically means like you break the task to smaller tasks
Hmm.
through having the knowledge of the world. That is actually what fuels all of these methods to
Hmm.
accomplish tasks that are very challenging, basically.
There was another paper that you identified called Mastering Diverse Domains Through World Models. Tell us a little bit about that one.
That paper, and also in that direction generally, is, but I would describe it in a sense that how you can bring more of LLM to this picture.
Hmm.
You can think about having Gen AI, or generative AI, to imagine things for you before going to accomplish a task. So let's say I have a robot, and the robot's task is to go from the point A to the fridge or to the kitchen, and the robot can actually build an imagination of this prescription,
Hmm.
okay, and put and consider that one as its goal. It's just the idea, basically. I mean, generic idea is, if I'm looking at you, and at the same time, just think about going to the fridge. I can imagine it, and
Hmm.
then that will be my goal. And then when I get up, I can actually, based on that imagination, considering that imagination as my goal state,
Hmm.
I can aim at going there. Okay, so that's one of the new concepts in reinforcement learning that LLMs can provide. Previously, I said that the agent does something. We have a video of it. We can caption that video and see whether the caption is aligned with the prescription. Here's
Yeah.
is other way. You give the prescription, the model actually imagines it, given the
Hmm.
context of the world, and consider that one as a goal state,
Hmm.
or goal trajectory, and then comes up with an algorithm to follow it. Okay, so that's basically one thing that is exciting these days, and you can train the model of this sort on many multimodal scenarios and many domains, and get a versatile like model which is able to tackle extremely challenging tasks through imagination and setting goal for yourself, or by yourself, I mean the AI agent can have a goal for itself and just follow that goal that is imagined, and over time the model is going to get better and better. So
Hmm.
that's philosophy of using Gen AI from other perspective, going from description to imagination. You imagine what you want to do and set that one as your goal and try to accomplish it. Another aspect is like you do something and then someone describes it for you and see whether the thing you did actually was right according to the description. So these are the two
Okay.
directions uh, that researchers are working on. Depending on the task, one of them is better than the other one philosophically. But at the end, when the models get bigger and the knowledge gets deeper, then that would be they can become almost identical,
Hmm.
except the computation side that we need to balance.
Got it. Got it. Got it. Got it. In your examples, you've mentioned robotics a few times. That's another area where there's been a lot of interesting work this year. How are you thinking about that part of the space?
So, in terms of robotics, as this interactive use of LLMs are heavily related to robotics. We can literally tell the agent that we want it to go to the kitchen and
Hmm.
literally ask the agent to consider goal state, and the agent goes there. These are actually recent works people in the area have been doing. That
Hmm.
your robot will imagine what would be the outcome that you're aiming for, and
Hmm.
and goes and accomplish that. So this your robot is supposed to pick up a cup, and you literally can say, "Hey, go a little bit to the left. You're holding in a bad way," or you can after you pull it, lift it up, you need to go to left or right and put it somewhere else. And these are things that we can teach the agent in basically robot in interactive fashion. So this
Hmm.
is like similar to the previous discussion we have had. There are works that people do use LLMs and Gen AIs in general for both imagination and also the description. There
Hmm.
is another area that sometimes people refer to as robotics, but sometimes as control. That this year and also a few years back have seen a lot of advances, I would say.
Hmm.
Uh, okay, let me put it this way. So in control, that is like the place that we again develop reinforcement learning agent to solve control problems. For those settings, many of the problems are not that flashy, so they don't make it to the media that much. But they have
Hmm.
been adopted a lot in industry and also in academic institutions. There are so much research in those areas.
Is it that they're not flashy, or that there are traditional control methods that are proven and work well? I always had the impression that it was more that than, that they're not necessarily sexy. I mean, I guess those two things are intertwined, but maybe the question for you is, given that for the class of control problems we have solutions that are well understood and based on heuristics, physics, those kinds of things, like, why are you seeing more reinforcement learning solutions being deployed? What are the advantages
Great.
of those solutions?
Okay, that's a great question. Let me give the example of that is actually currently being used. We have these are not jets, but these are small planes, but
Hmm.
they're fast planes, and they
Hmm.
have wings. Okay,
Hmm.
and when we deal with controlling the wing, so you need to uh, put a lifting force to the wing
Hmm.
to turn it in order to
Hmm.
stabilize the plane.
Hmm.
Okay, traditional methods have been working very well,
Hmm.
and they are so much approximation. You know, when you have a wing which goes through the fluid, we have a ton of turbulent interaction between the wing and the air around it.
Hmm.
Okay, so in order to solve the turbulent flow around it to see what is the optimal behavior of the wing, for each second you might need like a month of computation
Hmm.
to come up with some. So if you want to really see how the air around the wing of such small fast planes evolves, we need basically a ton of compute, and we don't have it because we need to make a decision and that fraction of a second. We don't have a month to design and understand what is optimal control. So what have been
Hmm.
people doing? They came up with a lot, like very nice and great working in practice approximation to approximate such dynamical systems.
Okay.
Okay, but all of them are based on approximation, and they're like
Mm.
years of engineering needs to go there to design or tune these approximation methods, and in the end you're not
Meaning
getting the
for
best.
new planes or new types of vehicles.
Yeah, for new planes and new types of vehicles you need to do the tuning again, but even for
Okay.
this given the wing, if you do the all the tuning, one AI agent easily can go and outperform it by like 30-40%.
Hmm.
And there
Wow.
are so many. Okay, these are, we are not talking about Boeing, we are talking about smaller businesses, and
Yeah.
the new industry people and stuff is spending like 5-6 years to tune those parameters. They just use RL methods,
Hmm.
get the really good performance, and move on. The same thing
Hmm.
is holding for IMU, for like sensor localization that we're using for almost everything on the planet. Your phone, your watch, everything has this IMU, which is localization engine.
Hmm.
All of these are based on approximation of traditional methods, but now you use reinforcement learning models and AI models in general to navigate those. Or for drones, that we before we had, I remember we could fly them in turbulent wind when the wind was like 5 meter per second.
Hmm.
With RL agent, you can take it to 20 easily.
Hmm.
5 minutes of training. So these are
Wow.
like things that are making big improvement in this area. But yeah, they are not LLM flashy, but they are immediately deployed in practice by industry.
And RL is a broad field. Are these examples here like online RL, offline RL? Is it traditional agent based RL or is it other types of RL?
No, these are the traditional concepts of reinforcement learning in
Okay.
RL. For this, for the drone setting,
Hmm.
these are all online. So you do offline pre-training,
Okay.
basically off policy setting. You do pre-training, but you need to, for these settings. There's another thing for these wind tunnel settings, that there is a wind blowing to the
Hmm.
drone. The wind is constantly changing and it's turbulent. It's not a constant wind is hitting. It's just
Right.
adversarially changing. It goes up, down, change the direction, and the wind is not just flat thing coming to the drone. You might have higher wind on the top, lower wind on the lower wind speed at bottom, and there are like many weird pattern
Hmm.
of wind that blow at this drone, and drone is supposed to go and do a very detailed maneuver. Okay, and this adaptation happens all online. These are
Okay.
online basic reinforcement learning, and it's policy gradient style methods. For the smaller jet and fast planes that I was talking about, the models I know, there are some model free methods, but this one I had in mind that is actually does adaptation very fast, and it gives like huge performance boost, is based on model based reinforcement learning. Actually, fun fact: the model based reinforcement learning for such problems is extremely fast and accurate, and
Mm.
you don't need to always go with model free for so many
Okay.
of these problems. If you have some ideas about the turbulent flow, you can go with model based. So these are literally traditional reinforcement learning
Hmm.
methods, but adapted and developed specifically for a problem at hand. So one thing in machine learning, and always I tell my colleagues across other fields who are not in machine learning, is in machine learning we develop concepts and algorithms, but for each domain we need to invent new ML foundation. If you're working computer vision, we
Hmm.
develop many ML foundations, architectures, problem setups. If you go to language, we do other stuff. If you go to voice and sound, we develop other methods, and
Hmm.
or music, we develop other methods. If you go to jets, Or if you go to airplanes, if you go to drones, if you go to like walking humanity robots, we need new algorithms and new foundations. These are different domains.
Hmm.
So if you design something very specifically dedicated for drones, you will get an algorithm which is extremely efficient. And
Hmm.
yeah, these areas are moving fast. Yeah, but yeah, they don't make it that much to the news.
Yeah.
But I'm excited about
Interesting.
those directions a lot.
Interesting. You identified the Aloha work as one of the examples of some of the progress that we've made in robotics this past year. And that's probably best thought of as like a series of work. This is Chelsea Finn and others at Stanford and maybe some other places. I guess to start things off, like when I've uh, read up on Aloha, and it's been in the news recently with mobile Aloha. It's like they're doing a lot of things. Like there's one aspect of it that's like a systems integration kind of challenge, and like creating these low cost robots. And at least for me, like the RL innovations kind of got lost in the mix of all the various things that they've done. There's like a telecontrol piece. And what's the core RL thing that they've accomplished with that paper that prompted you to bring it up?
Yeah, that's a good point. In robotics settings, building the robot and getting it up and running is a huge task.
Hmm.
So which they did a great job on that. From RL side, the part that is fascinating is
And
this
maybe let me
interaction.
interrupt you and have you explain a little bit about the project and the robot that they created and what it's able to do. And then with that as context, you can talk about the RL magic.
No, sure, sure. So they have this robot, the new robot that can interact with the world they created around it. The task is there are many tasks like folding stuff on the table, opening a door, walking around by walking, I mean moving around and in open areas. So that's basically the setup. And the robot is extremely agile, meaning that it can do things fast and very uh, it can do various stuff. It's not just one thing, folding shirts and stuff. It can go do many things. So
Hmm.
that's a setup. But the RL part that is exciting, and I think is a direction that's is going to help develop the future of robotics in many aspects, is the interactive part that you can interact with a robot using like recent technologies in generative AI.
Hmm.
So that aspect that you can interact with the earlier topic we discussed, that this new foundation or a new uh, novelty of using LLM in reinforcement learning and robotics is interaction. And in this work, they actually do interaction with robot in a language sense. So
Okay.
that's a part that is novel. The rest is developments that have been happening in the field in the last many years, and the fact that they could have this agile robot that can take on many tasks and deploy LLMs and being interactive with the user or the instructor, the person. That was the novelty that they have had, and we will see more of it.
What's an example of that interaction? The examples that I've seen, like it's you have a person. So a big part of what they've done is like imitation learning. So someone is essentially controlling the robot to do the task that you want the robot to do, and then after a few times, much fewer than previously, like the robot knows how to do it. But they're using like controls as opposed to, I didn't see like the language part. How does language come in?
Yeah, by language, I'm referring to all the Gen AI here as LLM. Okay, that one thing that is very important here is that they have been doing, and also it will be the direction that would, in terms of prediction, I think is going to be the way that we will develop our robotics agents. Is you do a lot of similar to actually the way we train large language models. Is we train them on
Hmm.
text, on passive text for like gazillions of data points,
Hmm.
and then in the end we do RLHF. We
Hmm.
tune them according to human feedback.
Yeah.
One thing here is this work is on that path is that you can do a lot of pre-training on human interaction or even on video in general,
Hmm.
and many of the past interactions that robots have had, and then in the end you can do RLHF style approach to just fine-tune the model. So they have
Hmm.
been doing their steps are in this direction,
Okay.
and it will be like the way we will be doing many of this robotics training, I would say.
Got it. Got it. So a big element of it is not necessarily that a human is interacting with the robot using language, but the robot has this linguistic resource that it can use for description of what it's seeing and for hints as to what to do next and how to interact with the environment. So in a sense, it's not necessarily seen in the interaction between the user of the robot or the robot and the environment. It's a resource that the agent can take advantage of, and the
Yes, yes,
API for that resource is language, among other things.
yes. So that's basically the foundation that used in the core of it will be used in the core of the algorithms
Hmm.
for robotics, that you can basically interact with the robot with using like basically language. So
Hmm.
that's one of the things that is going to enable robotics in the years to come.
Got it. Got it. Awesome. Awesome. Another theme that you identified is the idea of risk assessment. And you've previously in the conversation, you've talked about, the last time we talked about, hey, is RL ever going to be used in production because it's so hard? And now you're like, RL is being used in all of these devices, planes, and all these production and commercial settings. And that raises some interesting questions about how do we assess the risk that the RL, doesn't do what we want it to do or does bad things. And it sounds like over the past year, we've gotten a lot more sophisticated in how we're able to think about and analyze that risk. Can you talk a little bit about
Yeah.
what's happening there?
Yeah, you brought up a great point. So there are 2 points in risk assessment, reinforcement learning. One of them is that you have this RL agent, let's say in small planes flying,
Mm-hmm.
and you care about the risk. How risky are they? Are they going to fail, or are they safe? So
Mm-hmm.
in that direction is mainly about safety and constraint satisfaction.
Mm-hmm.
There's another which we have been working. I mean, the field has been working on it, the community has been working on it, and we have so much improvement, and the new methods are so good that they barely like violate these constraints.
Mm-hmm.
Another setting is you actually have a lot of risk in your outcomes. It's not about just a RL agent. Let me give you an
Mm-hmm.
example. In the stock market, if you have a policy which does the trading,
Mm-hmm.
or in healthcare that you have a policy which does the measurements, there are risks in the outcome itself. Like you might in the stock market you might actually sell things or buy things, but on average you might do well with some risk level.
Mm-hmm.
And the question is, can you develop a model or policy which gains a lot of money, let's say in the stock market or hedge funds, that gains a lot of money, but at the same time making sure that your risk is not high. So basically, you do reinforcement learning with the objective of minimizing the risk. And risk is like a
Mm-hmm.
variance of your reward, or variance of dollar value you make per day. So that thing is like,
To restate that, historically, RL is about optimizing an objective function or a loss function, and that loss function is usually expressed in terms of some average, an expectation. And What that doesn't then capture is the associated risk in meeting that expectation. And you're saying now we're getting more sophisticated into incorporating those risk factors into the reward function itself.
Yes, yes, yeah. One of the traditional example a friend of mine used to give was, let's say we come up with a policy which increase is an RL policy,
Mm-hmm.
which is optimized and trained to maximize the average wealth of, or the global, basically wealth of United States people.
Mm-hmm.
And after deploying it, we are saying, hey, we increased it by 5%. And then you go
Mm-hmm.
and look at it, it's like top 1% got lot richer than bottom 99%.
Mm-hmm.
Okay, so that was not the outcome you wanted. You just said
Mm-hmm.
you wanted to be like, you want to increase the wealth of the nation,
Mm-hmm.
but the risk was, if you look at the distribution of reward, there are small, tiny, teeny number of people, they got a lot of money, and the rest of the population didn't get that much money. So that's like basically a risk. And we got, yeah, sophisticated enough that in banking, in healthcare, we actually go after optimizing for risks directly and considering those in our algorithms,
Mm-hmm.
because it just matters. Like in healthcare, you don't want to improve the outcome of your policy or prescription method that on average increase the health of the people by 5%. You don't want
Mm-hmm.
that, because if that happens, there's a possibility that you just killed so many few,
Right.
but you just gained many more. So it's just not the right metric to look at, the average reward. So taking a look at the risk
Mm-hmm.
is now bread and butter in these domains, specifically in premium design, sorry, in insurance companies
Mm-hmm.
and stock market and healthcare. They care a
Mm-hmm.
lot about these things. And speaking of which, insurance companies, people in insurance companies were the people actually started writing mathematical books about risks in 60s, 50s. So
Mm-hmm.
the whole idea of risk was, I mean, it hasn't been, did not emerge from there, but they were
It's
pioneers of it.
foundational
And
to insurance. Absolutely.
yeah, so many risk functionals that we have in this in reinforcement learning that are named after insurance policies.
Hmm.
That's how influential they
Interesting.
were. So
Yeah.
they care a lot about risk everywhere,
Mm-hmm.
and they know the value and importance of AI and reinforcement learning. They
Mm-hmm.
are bringing these ideas to their settings. Okay, when I say they bring these ideas to these settings, I don't mean all the insurance companies are like that. They are starting.
Sure.
That needle is tilted. They
Yeah.
were not doing it, now they're doing it. Same as banking and healthcare.
But part of what's interesting here for me is that you're speaking about this in the language of risk, but it also has clear implications to fairness and responsible deployment of RL algorithms.
Yeah, that part specifically in healthcare and
Hmm.
loan allocation, it becomes extremely important. These are areas that you will not be able to mathematically model. So when we're talking about these concepts, we need to read the book, and we need to read the law and see, based on law, what are the things that are actually compliance with the law. And for that, it's not, the law is not based on mathematical equations. It's just very weird thing from
Hmm.
people like me. From our perspective, it's just so much details in it that lawyers needs to parse it for us. And when we parse those, then we need to turn those to mathematical formulas, and that's the part that is extremely hard. But if you do that, you would get something that is functional and useful in practice. I would say at the moment, the models are getting to be really good, but people in this industry that are working towards these concepts of fairness and understanding and interpretability. Okay, moving in these directions, but we expect to have more and more of these in the future, because when these companies start deploying RL agents everywhere, we need to have more of the Congress forcing to go there, and
Mhm.
make sure that these things are complied. At the moment, we are a little bit slow because in the country we have so many issues that people are taking care of. But we should start allocating resources to these cases where reinforcement learning is used in practice, specifically in healthcare and banking systems. And we need to have clear cut laws to navigate
Yeah.
these companies.
What I hear you saying is that there's broader societal work that needs to happen to align on the right way to think about these rewards. And in parallel, the RL community is trying to get more sophisticated in the way that factors like risk and responsibility can be expressed in rewards functions. And so hopefully when the society gets there, the technology will be better equipped to be able to implement it.
Yes, 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 and we would get much more. I mean, the field or the people working in this area would get much more attention when these companies start making a lot of impact to the society, and then we need to have immediate response to come up with new laws to navigate these companies who are trying to improve human life status.
Let's maybe shift gears and talk a little bit about the future and how you see things evolving. I imagine that, just kind of getting started in this conversation about the future, we're just getting started in integrating LLMs into RL. You've said as much. But I imagine that that's one of the big things you see moving forward.
Yeah, certainly. The use of basically two paradigms that we already talked about it, but we can visit one more time. One of them is the fact that we use LLMs a lot in our, or Gen AI in general, a lot in our RL formulation and our algorithms, both in terms of imagination and also description,
Hmm.
instructing the RL agents to work in practice. So that's one general theme that we are going in those directions, and I'm excited about seeing new works and capabilities coming out of it. Yeah, I'm not going to predict in 2 years we're going to have robots at home, but it feels much closer than I used to feel like a year or two ago.
Well, when you look at a system like mobile Aloha, and we'll put videos, some maybe demo videos or something in in the show notes page. When you think about a system like that, do you think that the kind of core remaining challenges are RL related, or are they systems integration related or mechanical? Like, is RL help us understand in the context of robotics how much of
Okay,
the delta between we're living in the Jetsons and where we are today is RL and getting that part right?
I might be a little bit biased, but if you ask
As an RL researcher.
yeah, yeah, but if you ask a person from mechanical perspective or like building robot perspective, they might say, yeah, there's a lot of work needs to be done to make the robots better. But for those, I think the roadmap, at least from my understanding, the roadmap is clear. If you want to make a really crazy agile robot, we have the physics and you can build it.
Hmm.
Okay, it's just a matter of building it. Is like we don't have, okay, we have open questions, but those are not open questions that have not been solved, in the sense that okay, the variations have been solved.
Another way to maybe say that is, we've got the various Boston Dynamics robots, but we're not setting them out loose to do things because the intelligence part isn't there. The mechanical
There you
part
go. Yeah,
is.
yeah.
Yeah.
Mechanical part. Yeah, we don't. Yeah, if we want to build it, we can build it.
Yeah.
The but yeah, of course, it takes extremely talented people in that area.
Not to diminish all the other things. Absolutely.
Yeah, but the RL part fundamentally we are lacking. We don't know yet. We can't. We don't yet have. Yeah, if you ask a person in the robot building side, okay, if you have enough money, and resources, can you imagine how to build a really fascinating robot? The answer is usually yes, they know how to. But
Hmm.
for us, if we still don't know, we're still doing actively basic research to
Hmm.
see what is the right way of designing like intelligence of the robot, and we are not
Hmm.
there yet, and these are open questions. Getting things working together is very important.
Hmm.
So nowadays that we have this new Gen AI technologies that are going to be used more and more in robotics. Getting those and seeing what is the right way of using those is an open question. We don't know how to do it. And as you know, in machine learning, we have a task. We try many ideas, and we see which one works, and we communicate with the rest of the field, which is the beauty of open research in machine learning. That
Hmm.
I should use this time and praise it. We should keep doing open research. It would help to basically many people will start working, well, keep working in this area and develop methods to see how what is the best way of developing this Gen AI accompanied robotics models to tackle like hard tasks. So that part is not obvious to us at the moment.
Hmm.
So I would say, yeah, that's the open problem that has not been. The similar version of it has not been solved, so we don't know. If we get a really good RL algorithm that can be used in robotics, and the robot can can achieve the maximum capacity, the day after there will be so many effort to build more advanced robots. But
Hmm.
the reason, the point, the problem we have at the moment is like the intelligence part of it is like very primitive.
And so, if you were to drill into that, you're essentially talking about reformulating RL around this, having LLMs as a tool. Can you identify specific directions that you think need to be explored, or specific kind of threads of research that you think are promising that you expect to yield fruit over the next, 1 to 5 years?
From theoretical perspective of reinforcement learning, we have so many algorithms that are provably optimal in the sense that given the assumption that we have, they're optimal. Okay. So
Hmm.
now we need to go and design algorithms, that optimal algorithms that when you give them the power of LLM, the power of this abstraction that we have, which also we need to mathematically define what these powers actually mean in practice. Sorry, in theory, we need to go and design algorithms that say, hey, given the fact that you have access to LLM or Gen AI tool, what is an optimal algorithm to be used for exploration and exploitation in
Mm.
the reinforcement learning setting? Okay, so that's from the theory standpoint. So theoretically, we need to reassess.
Yeah. So to restate that, in traditional RL, like we're at the point where we can analytically quantify the expected performance of these algorithms. Like there's an equation that you can write that can say if you have a good algorithm or not. In terms of incorporating our LLMs and Gen AI, we're at the stage of kind of getting it to work and showing examples, but not really saying how good it is beyond benchmarking against other things. And you're saying that from a theoretical perspective, the next thing is trying to be more rigorous around describing the performance of these LLM based RL systems. Do you expect to be able to do that? Like, do we even have good theoretical foundations of LLMs independently? And do you need that in order to get to the level of rigor you're describing with RL thrown into the mix as well?
Well, that's an open problem. We don't know yet uh, how to formulate it as an open
Got it.
question. That using this, given the presence of LLM, how to formulate it, and that's a question that I've been talking to some of the old colleagues in the who were like classical reinforcement learning researchers,
Hmm.
who are still classical reinforcement learning researchers. They are all, the only thing we converse is what is the way to do it. I don't know, but one thing I know is traditionally, when we were not making such an assumption of having
Mhm.
access to LLMs, we developed so many algorithms that are optimal and blah blah. But in the end, there are recent works that actually show that just stochastic gradient descent that we have been using before is as optimal as all of them. So, meaning that all these algorithms that we have developed, because we were not making any assumption about the world, we were like generic world, no assumption you can build an airplane in the kitchen setting that has no idea about anything or any abstraction or knowledge of the environment.
Mhm.
Those algorithms that we have developed, they are as good as, you might call it dumb algorithm, but it's just
Mhm.
very smart. It's just SGD that we
Mhm.
have been using forever in the in reinforcement learning recommendation system. Like if you look at Amazon
Everything.
recommendation system, it's
Yeah.
based on SGD. It doesn't use any of these advanced RL algorithms that we are
Mhm.
doing. It just does SGD. But these recent works actually show that SGD is actually optimal RL algorithm when you don't make much assumptions. Okay, so
Mhm.
but now that we are having this LLM in the picture, would you say SGD is a smart algorithm?
Mhm.
I
Mhm.
would say I doubt. So for when you have LLM, I don't think SGD would be the optimal algorithm. We need to have intelligent algorithm which directly goes and utilizes the presence of um, the LLM. And one of the directions that some of us are excited about is related to information gathering. Many of the RL algorithms before were greedy about not losing.
Mhm.
That's literally the way you can describe them. They were like extremely greedy about minimizing the long term loss.
Mhm.
So that was basically the core of all these algorithms. But if you have LLM, you don't need to be that greedy. You can look at the future and decide, hey, should I ask some certain questions from the LLM for a given task to gather information and understanding about the world before becoming greedy to minimize the future loss, or I should go directly for the future loss. That's a point that I think it would enable us to develop a new foundation for reinforcement learning, having access to this knowledge abstraction models.
So, kind of put another way, classically, one of the big challenges or variables, like depending on how you put it in RL, has been, balancing explore and exploit. And it sounds like you're saying that these classical approaches have tended to be more exploitative, maybe. And now we've got this new tool to help us balance explore, exploit, and explore more intelligently, as opposed to
Exactly.
either you know I guess the knob that we're using to balance these two is not like one, essentially one number, like a percent of time. It's situation dependent, state dependent, that kind of thing. It's much more nuanced than was previously possible.
Yeah, indeed. That's exactly the setting that we have this abstraction. It can be used to direct our exploration to be extremely informative.
Hmm.
Yeah.
One of
So
the things that you said a moment ago um, triggered a thought for me. You talked about how we have all of these RL algorithms that don't have world knowledge, and it made me think about generalizability as kind of a challenge that RL has faced. Meaning, one of the reasons why we have all these algorithms is one does really good on Atari games, another is really good on Minecraft, another is really good on Soda or whatever, or Dota rather, not Soda. But uh, it's been a challenge to have like a general purpose algorithm. Is that still the case without LLMs? And to what degree do LLMs change that?
okay, so that's a great question. For each domain that you refer to, we have been developing a specific algorithm for.
Mhm.
Okay. And back in 2014, 15, and 16, our one of our main goal was to solve games.
Mhm.
And if we keep that goal of getting better at games, yes, LLMs can actually come to the picture and help the agent to basically help the models to or RL agents to do a better job in learning. When the agent is dealing with Dota, the agent doesn't need to start from scratch.
Mhm.
Now we have millions of videos out there. We can describe exactly by using LLM each agent is doing and come with a strategy and describe it. And this is going to help us to speed up the RL agents when we are dealing with different games. However, in last year or two, or even further back, the whole focus has shifted a tiny away from game solving. Um, if you remember 2016, 17, 18 was just everyone was like in reinforcement learning. Many people in reinforcement learning were very involved in solving Dota, solving uh,
Yeah.
Go, chess, these things. But now the focus is a bit shifted to more real world applications that we can improve human life directly after
Mhm.
building all this foundational knowledge uh, by tackling Go or game of Dota. So we are actually going more towards like being more domain specific, for which LLMs would help. And when we do domain specific things, we probably would not have one model, or we don't aim to have. It's not. It doesn't make much sense to have one model which is able to do stock exchange optimal policy development at the same time is able to
Mm.
fold mm, I
Full
don't know,
clothes.
clothes and
Cut
clean
apples
dishes.
and
Like I'm like
yeah.
maybe not the best idea. So we are getting more domain specific, and each sector of academia and industry is focusing on one of these directions. However, one thing very important about the time that we have been doing a lot of games is the the expertise and knowledge we have developed. That thing we should not ever forget.
Mhm.
That's the reason we have many of these LLMs is because we have done a lot of work in Atari and Mojoko, and that those are like precursors of the RLHF is one of the algorithms that people developed. The algorithm used there is one of the algorithms that is being used in one of the works that tackled Mojoko robotic tasks back in
Mhm.
I don't know 17. Or the foundation of AlphaGo taught us a great lesson. Both AlphaGo and TD Gammon algorithm, both of them, also DQ, and all of these taught us a great lesson that when you develop a reasoning algorithm and you care about reasoning a lot, you will have a hard time putting all of it in one model. So
Mhm.
when you play the game of Go, we tried a lot for years to train one model, uh, which takes input as a state of the game and outputs the next move. We tried a
Mhm.
lot to do that, but this is a reasoning task, and we learned that if you want to do reasoning and if you want to train a model which given the input state tells you exactly what is the next move, that training such a model is going to be extremely expensive. But
Mhm.
AlphaGo taught us we can, and also some other algorithms based on UCT, which is upper confidence tree search, taught us you can balance, in order to get optimal reasoning, you can balance compute and model size and data size. So
Mhm.
instead of having one model which is able to tell you the next move, you can actually run a tree search computation and see if I make this move, what happens? If I make this move, what happens? If I make this move and then this move and then this move, what happens? So you just build a tree locally, do a little computation, but at the branch of a tree, you can ask what is the average good move after that. So you can actually use these types of state-based reasoning to
Mhm.
gain a lot of intelligence. And this lesson that we learn, I think, would be at some point useful for LLMs when we want to make LLMs to be more intelligence in the sense of reasoning. So
Hmm.
at the moment, the LLMs, you give the input sequence, they output output the next word. But if
Hmm.
you use LLMs to build that tree for themselves, see which, like, making many trees and see which one actually is more reasonable one, you can gain your intelligence exponential with exponential improvement by just doing that instead of making your LLM model bigger and bigger and bigger.
Hmm.
So that's a great lesson that we learned from AlphaGo. I hope that I would see that would be one of the steps in the future of LLMs, that we, instead of having them as a reflexive model which takes the input directly output the solution, make them a combination of state-based model and reflexive model. So you can have
Hmm.
LLM to predict many possible outcomes and evaluate each, and then come up with a solution which is the most reasonable one. So this way we can gain a lot, like, good amount of boost in intelligence behind these
Hmm.
models, which is a lesson we learned from AlphaGo and a few other great works in the past.
So historically, RL was seen as this really promising element of the journey towards AGI, in the sense that of all the ways that we do machine learning, it seemed to be the one that was most, uh, similar to the way babies learn, is kind of the classic analogy. And in the game setting, having an intelligence that can excel at lots of different games, like, supported that idea. It's like, okay, we're starting with, trying to create this intelligence that learns like we learn, that's good at one thing. Now let's make it good at other things, or a broad set of things. And now you're suggesting that we've reached a level where we're now trying to put these into practice and practical use more, and that kind of by definition de-emphasizes broad cross task generality. Do you think that that slows progress with regard to foundational LLM, I'm sorry, foundational RL capability? Not necessarily that AGI needs to be your goal, but trying to get to general intelligence has propelled a lot of innovation. Like, do you think that by focusing on kind of these narrow commercial use cases, that slows innovation overall for RL?
Yes and no. Yes, in the sense that,
We'll be busy making money, so.
yeah, that's one thing. The bright minds in this area, they will go and work on different subjects, and each subject is going to, as you said, it requires to generate revenue and money and stuff. And they will make progress, but eventually, after we make great amount of progress in each of these directions, we start merging things. That has been always the case in machine learning. You push in one direction, some other friends or colleagues they push in another direction. At some point we meet, we merge. Okay, and we keep doing it, and then the merge happens bigger scale and bigger scale and bigger scale. You can see in, like, in LLM, in NLP, natural language processes, we have been developing many ideas and many architectures. In computer vision we were doing the same thing. At some point we merged them. Okay, the
Hmm.
merge at some point, sometimes the merge happens. Now we're using transformers for both domains, similar
Hmm.
ideas, similar architectures.
Yeah.
So from that perspective, I think is best thing to do at the moment is to go each people, let the people naturally go in directions that excites them, and develop algorithms for each of these directions.
Hmm.
We can also take the other direction of all of us keep working on these foundation things, but I think compute wise we're not there yet. So if you want to go in direction of having a AGI that it reinforcement learning based algorithm that actually is able to solve many of these multimodal problems in many directions and many sectors, and sciences, and also engineering.
Hmm.
We if you want to train that thing right now, we don't have compute to do that, and
Mm.
that thing would also be required. Yeah, we don't have compute for that. We need to have we need to take the other route.
That's an interesting statement. So you're, and maybe it's not interesting. I mean, because again, going back to like our first conversations, like you said then, RL is all about compute efficiency and trying to see how much juice we can squeeze out of the lemon, which is our compute. Like you said that, I don't know, the first time we spoke like 5 years ago maybe. But you're kind of also saying we've kind of squeezed all the lemon out of the juice, all the juice out of the lemon for where we are for our broad goals. So now let's go in these more narrow directions where there's still, there's value in, applying this technology and these ideas. There's plenty of value there. Let's go in those directions. And a little bit of it sounds like, hey, take a breather and let's let compute catch up for us or catch up to us.
Yeah, we should wait for compute to catch up for us, and at the same time, for each of these subdomains, we need to go and develop domain specific algorithms. And these domain specific algorithms that we develop always allow us to, okay, in science, usually when we go in different directions, this is actually, I think, Richard Hamming was saying in one of his talks. You go in one direction and you develop so many things,
Hmm.
and you can develop so many things because you see so many things in that specific domain that inspire, or
Hmm.
basically the answer is in the problem setup. And I work in another domain that is answer is not that clear. But when we talk to each other, you tell me how you solve that problem. I'm like, hey, the same solution actually works for me here
Hmm.
for this other problem setup. And then I
Hmm.
take your ideas and apply to this new domain, and I advance my domain. And then
Hmm.
the new things science shows me and the problem setup shows me, or I come up with new foundation, and I see new observations or new keys to solve
Hmm.
more advanced problem, and I solve it, and then I tell you, you're like, hey, you can actually do that. So I
Hmm.
gave you two people problem, but this happens in broader sense across like millions of researchers. And that's one of the ways that research has been evolving. Come up with an idea in geometry in mathematics, prove so many theorems. You do so much in number theory, and then we meet and we are like, hey, if we just change our terminologies, in I can use all these geometric tools and theorems that I have proven. I can use this adaptation of terminology and bring to number theory and solve many many open problems in number theory. And this had
Yeah.
happened many times in history. Most of the
Hmm.
advances in mathematics happen this way, same as engineering and same as other branches of science. Here for reinforcement learning is we go and solve these domain specific problems, and along the way we develop new foundations that actually allow us to make things to work. And over time we communicate with each other and come up with a solution that the solution I come up with for one problem I can tell you, and you can say, or maybe it works for your case too, and we just keep doing it and come up with the generic ideas. But at the same time, since the community is talking to each other a lot, the unification happens very quickly. It's not like 1940s unification that used to take like many written letters to happen. Now
Yeah.
we just take a phone and call, and the communication happens. And you see, it's not now. Many researchers are using transformers in their architectures because we just communicate with each other, or
Sure.
many researchers are using LLMs in their settings. So we just keep doing
Yeah.
it and keep getting better, and just communicate the things we discover with each other, and hopefully we will have a really good foundation soon.
Hmm. On this idea of compute being the limiting factor, do you think what's required? Is it incremental innovation, meaning, going from, you know, 10 nanometer processes to 3 nanometer processes, that kind of thing? Or is it like we're not going anywhere till we get quantum computing?
I would say the former, to be optimistic, because quantum computers are not there yet. If I said the latter, it would be like,
That
okay,
would be
we have,
pretty bleak.
yeah, it would be like we need to wait for way longer. Yeah, I hope it's the former one. The amount of compute we need, okay, of course, if we have more compute, we get more intelligence. That's
Mhm.
like a no brainer. Uh, that's been known
That's what we've seen.
centuries. Yeah, we have also seen it here many times.
Yeah.
But yeah, we know there are in decision making. If you build a really really long tree, you or deep tree, you can solve it for many of the decision
Mhm.
making problems. The problem is we can't build that tree of
Right.
knowledge. So the question is like at the for the current need of the society, how much of intelligence we need. I would say at the moment, if we get better GPUs and
Mhm.
faster GPUs, that actually there are many
You're
people.
not
Actually,
biased at
also at
all.
Nvidia, there are many people actually day and night are working to get better, improving GPUs. So GPUs are improving.
Mhm.
They are hopefully getting more accessible,
Mhm.
and many people can have their hands on them. And this way, we can develop algorithms that can run faster on these GPUs.
Mhm.
And then if we can do very good reasoning based algorithms and build these reasoning based algorithms on using LLMs and generative AIs, AI models, we should be able to get sufficiently good and reasonable AGI, which is able to do the task of reasoning. We should be on the right track. So the
Mhm.
improvements from algorithmic side are going to be mainly incremental, and the compute side also going to be incremental. But I'm not, okay, what I hope is not getting billion times faster or better in compute. If we get like any factor of like 10 better, we should be able to tackle really really
Mhm.
challenging problems that are exciting. But at this point, I would say one of the, I think we talked about this one at one of our earlier conversation. We need more talented people to work in AI and reinforcement learning. We have
Mhm.
amazing people working in this area, but we kind of need more. And there's a there's also, there are many great people. uh, I'm not talking myself, but great people leaving academia. So we need to also find a way to teach the next generation,
Mhm.
which has been a problem
Mhm.
that I'm seeing right now. That since we have academia lost many people who were working reinforcement learning to industry,
Mhm.
and it means that we don't get that many people being trained in these areas, which is kind of problematic. We need to also, well, but community and society would find a way out of it. But if we can help those things, that would be also helpful. It would have been great to have many reinforcement learning students graduating and joining the either academia or industry to advance these directions.
Mhm.
I'm not gonna be
Mhm.
pessimistic, but I'm saying that it would have been better. We don't have it, but it's all right.
I think we could go into, the different conversation, maybe beers or whatever, but there's a whole,
Yeah,
is it academia push versus industry pull, and probably a lot of that pull right now is happening, towards LLMs as opposed to RL, which is not making things easier, I think, for RL as a community to advance. Although I guess the converse is that, or the flip side is that LLM is this amazing new tool that we can use to make RL better. So.
yeah, 100%. Well, also one thing a machine learning community has shown is like we can switch direction of a study in one day. Like if yeah, in 2016 to 17, I think we had quadrupled the number of
Yeah,
papers submitted to NeurIPS in related to reinforcement learning. So the people in machine learning are extremely amazing
agile.
and
Yeah.
very agile, similar to many other fields. And yeah, at the moment, yeah, we have smart people working on LLMs. We will get it to a great point, and we will start more working on other subjects until we pick a direction that is very exciting for anyone who is excited about anything should be able to work on it, and that has been the
Yeah.
case in machine learning, which is great.
Yeah. Awesome. Awesome. Well, Kamyar, once again, amazing conversation. I learned, so much from your notes and then digging into it with you, and I'm sure our audience has as well. Thanks so much for joining us once again to kind of talk through the progress we made and talk a little bit about the future.
Yeah, thank you, Sam, for having me, and it was fun chatting with you once again, and looking forward to future talks coming out of your podcast, and also hearing from you and your team in the future.
Awesome. Thanks so much.
Thanks.